Okay. So let's look at this picture and say that red graph that you see there, you can see I have it labeled as velocity and time. So let's say that red graph is the velocity of an object over time. Okay? Now, let's define big F of x obviously I didn't plan this very well. There, that should work okay. Let's define big F of x as the integral 0 to x v of t dt. So can everybody visualize what that's doing? That's your accumulation function. The starting time is 0, ending time is x. So for example, if I asked you what f of 1 is, you would say what? What does that integral on the right represent, just geometrically? I agree. Anders says triangle. It should be the area under the curve, right? And from 0 to 1, the curve is a line. And so what's the area under that line down to the x-axis? It would be the area of a triangle. It'd be 1 across, it'd be 2 high. Area would be there we go. Does everybody see it? It's a triangle, it's 1 by 2. Area is 1/2 base times height. But the main thing is, does everybody see that when I evaluate this big F at 1, then by definition what I'm doing is making that upper limit of the integral a 1. And since in this function, or in this example, this function is positive, I would definitely interpret that as area under a curve. Okay, now, by the way, what else does this tell me from what we just learned yesterday? I know the integral from 0 to 1 v of t dt is any antiderivative of this function. Okay, what's the antiderivative of velocity? What's the antiderivative of velocity? Yeah, position. Good. And there would be some plus c, right? But of course our fundamental theorem says grab any antiderivative you want. So let's just grab the one when c is 0, which would just be the position function. And what our fundamental theorem said is, if you want to evaluate from 0 to 1 the integral of v of t, you just find the position function, you evaluate at 1, and then you subtract what you get when you evaluate at 0. Well, what do you get when you take the position at time 1 minus the position at time 0? Doesn't that give you the so-called displacement over the 0 to 1 time interval? Does everybody agree? In other words, I would interpret this 1 that we got, which was the area under the curve, as the displacement during that time. And of course, since the velocity is positive, That means we're always traveling in the same direction over that time interval. That means I would interpret that 1 as a distance traveled. Okay, so this is what we mentioned the other day. If your velocity function is positive and you integrate from one time to another, the answer you get, which would be area under the curve, would also be interpreted as distance traveled. So from 0 to 1 second, this object went, let's say, 1 foot, if this was all in feet and seconds. With me so far? What's f prime of 1? Okay, Ethan says it's little f of 1. Everybody agree? Okay, and Andrew says that's 1/2. Well, let's see. First of all, when we say f, little f, we are talking about v in this picture, right? Yeah, what's v of 1? Look at your picture again. Yeah, definitely 2, right? Does everybody see how we're getting that? Again, we're saying that if f of x is the integral 0 to x v of t dt, then our first fundamental theorem of calculus says if I want to take the derivative of that accumulation function, it should just be this little function on the inside evaluated at whatever that limit is, that x. Well, in this case, that would be v of x. So what's f prime of 1? It's v of 1. And in the picture I can see v of 1 is 2. Alright, so this is the funny thing. Remember, the function we're talking about, this f of x, is not the picture you see up on the screen. The picture I see on the screen is v of t, correct? F of x is this accumulated area function that I don't have a picture of up here. So I'm just asking you questions about this big f of x we can't see based on the v of t you can see. And every question I'm asking here, I can get the answer from looking at this picture for v. So here's the thing. If I ask you for values of big f of x, it looks like those are areas under the curve of this v function. If I ask you for values of the derivative of this big f of x, then they are actually values on the graph of the v. Does everybody see that? This one is areas under the curve. This one is actual values on the graph of v itself. That's the difference between the two. Here, let's ask you another one. What's f prime of 8? Everybody agree? F prime of 8 should be v of 8. And clearly in the picture, that's one of the places where this v function has a t-intercept, where it's 0. What's f of 8? Okay, Tim says 11. Now one thing is for sure, one of these is that actual v value that I see in the graph, right? And that's supposed to be this one. What is the f of x supposed to be measuring again? Yeah, okay, so let's write that down. Ethan says it's the area of the trapezoid. Remember that the f is the accumulation function. So if I ask you, what is f of 8, we're simply asking, what is the integral 0 to 8 v of t dt? Well, if you look in that picture, there's clearly, an x-intercept or a t-intercept at 8, which means I would interpret this integral geometrically as the area under that trapezoid. Now, do you see that that trapezoid could be split up into 3 parts? there's the integral from 0 to 2, which would be a line function. It would actually be y equals 2x. Then from 2 to 5, your function is just y equals 4. And then from 5 to 8, you've got some kind of negative slope linear function. But since I know this should just be the area of a trapezoid, I should be able to just get the area of the trapezoid by doing what I know about trapezoids. What's the area of a trapezoid? It's 1/2 height times base 1 plus base 2. The height is 4. What are the two bases? The bottom base is 8. The top base is 3. Looks like I get 11 halves, or 5.5. Rebecca says, are we talking about little f? Well, right now with this one, in both of these, we're talking about big F. And what if the interval doesn't start at 0? Well, of course, I have to define this f of x, this big F of x up front for you, or you define it in, in the context of the problem. But if I started that at a different point, it would obviously change the value of the integral. So if I define the f of x to be integral from 1 to x v of t dt, then all these questions I'm asking you would change. So for example, if I asked you what's big F of 1 now, you'd say 0. If I asked you what big F of 8 was, now it would be the area from 1 to 8 instead of the area from 0 to 8, and you would just get a different area. So yeah, it's going to be determined by the context normally. And you notice in this sort of a problem, if this was really a velocity function, we would probably almost always start that interval at 0, if that's when we started tracking the movement of the object. So yeah, it's always going to be determined by context or simply given to us as some particular starting point. Okay, now question. So we came up with big F of 8 was 11 halves. That's the area under the trapezoid. By the way, how else would I interpret this? I would say this is the displacement of the object over the 0 to 8 time interval. So in other words, the area under that curve, which is 11 halves, is also the distance traveled by that object in that 8 seconds. Okay, what's the other thing we came up with? The derivative was 0 there. What's the derivative of the big F at time 10? Yes. Okay, now let's back up a second here. Let me ask you, what's big F of 5? I'm sorry, F prime is what I mean to say. We can calculate F of 5, but that's not what I meant. F prime of 5 is what I was after, sorry. Yes. Okay, what happened here when you went from 5 to 8 to 10? When you're looking at F prime, here you had a 0 at 8, and then over here at 10, you were negative for your F prime, and over here at 5, you were positive for your F prime. What does that tell me about what's happening with big F? Okay, it is a summation. Rebecca says decreasing area. Okay, I agree with what you're both saying. What I was thinking of is what happens when your derivative goes from positive to negative through a point where the derivative is 0. what's happening at that point where the derivative is 0 if that derivative is changing signs on both sides of that point. It would be an inflection if it was a second derivative. Okay, Ethan says it becomes negative area because what he's thinking of is once I pass 8 and I start accumulating area under that bottom triangle, the one that goes from 8 to 15, that will all be counted as negative area, right? Which means when I start summing that stuff and accumulating it with the area that I already had under the trapezoid, I'm going to be subtracting area. In other words, what did I do from 0 to 8? I added up positive area, but then once I hit 8 and go from 8 to 15, I'm going to start subtracting area. Okay, so Andrew says, then there should be a maximum at 8, shouldn't there? If from 0 to 8 you are adding up area, but at 8 to 15 you start subtracting area, then isn't it going to be the case that at t equals 8, you're going to have a relative maximum on the total amount of area accumulated? You were adding it up from 0 to 8, but then starting at 8, you begin subtracting area. That means at 8, you had accumulated a relative maximum amount of area. Does that make sense? Now Ethan says, if the integral is displacement for a velocity graph, what would it be for a position graph? Okay, there's no nice, nifty interpretation like that, okay, because in the case of v of t from a to b, okay, why can I interpret that so neatly as displacement? Because I know what the antiderivative of v is. I know the antiderivative of v is position, right? Is there any nice, useful interpretation of position that we've ever talked about? Or more to the point, have we ever talked about any function whose derivative was position? See what I mean? So let's put it this way. For me to interpret an integral in a useful way, I have to have an antiderivative of that function I'm integrating which is useful to me. Now that means what? And this goes with something James said. If I was integrating acceleration, for example, so if this graph that we're looking at was an acceleration graph, then the answer I would get would be a velocity, and it would be a total change in velocity over the time interval. Similarly, if I integrate velocity, I can get position, but since there is no real useful interpretation of what happens when I integrate position itself, that one we're never going to see, because it just really doesn't tell me anything. But back to what Andrew said, and this was the big upshot here, I would say big F has a relative max at t equals 8. And again, that's because your big F went from increasing to decreasing, which means there was definitely a relative max at 8. And again, you can see that in the picture. You're adding up area all the way to 8, then you start subtracting it. Makes sense, doesn't it? If you calculate any of the f prime values from 0 to 8, you can see that f prime is positive on 0 to 8, because f prime is just v values, and the graph of v is entirely above the horizontal axis from 0 to 8. Well, a positive derivative means that f is increasing, which is definitely what's happening from 0 to 8. You're adding more and more area. The area is positive and it just gets bigger. But what happens on the interval 8 to 15? Well, now your first derivative is negative because all of those v values are negative. But that simply tells you that big F is decreasing, which of course is exactly what's going to happen. You're starting to subtract area now, and it's going to take away from that positive area you had already accumulated. Let's ask you, okay, what did you say f of 1 was? You said that was 1. and you said f prime of 1 was 2. Okay, this one was because v of 1 was 2. This one was because the area from t equals 0 to t equals 1 is 1. It's the area of that little triangle that we looked at in the picture. What's f double prime of 1? Now's the time to ask about that second derivative. F double prime of 1. Okay, Ethan says 2. Does everybody see where he's getting that from? It's not the same reason that one's a 2. This one was a 2 because f prime of 1 is v of 1. Okay, why is that one? Because we're saying f prime of x is f of x. So that means if I ask you what f double prime of x is, what should that be? It should be little f prime of x, which in our case would be v prime of x. Yes. Of course, what is this? It's also acceleration. And when you look at this velocity graph up here, how do you get acceleration? Don't you look at the slope of the velocity graph? And does everybody see that when you get to t equals 1, the slope of this graph that you're on, that is this little part of the trapezoid, is definitely 2? I'm just thinking about that line being over 1 up 2. The slope of that line itself is the acceleration, and that is the second derivative of this accumulation function. So here, let's try a different one. Tell me what f of 5 is. And that's the one I started to ask a few minutes ago, and I didn't finish it. Let's do f of 5. Okay, Brittany says 13. James says 4. Ethan says 16. Okay, is that the piece we're talking about? And now Brittany says 16. I could definitely decompose that area into those two parts. And of course, what's the height overall on that rectangle part? That's supposed to be 4. So I can definitely see the purple rectangle is 3 by 4. That area would be 12. The area of the triangle that looks like that would be 2 times 4. So that would be 8, but it's a triangle, so half of that would be 4. And we know that the accumulation function is definitely the accumulated area under the curve, so I think 16 looks right. F prime of 5, we did that one before. What's f prime of 5? Okay. What's f double prime of 5? Okay, does everybody agree with that, or does anybody disagree? Yes, weight is the right answer. dne. Okay, does everybody see why it's dne? What is f double prime? It's the slope of the graph you're looking at. That is, it's the slope of v. Does that graph you're looking at have a slope at t equals 5? What's happening there at t equals 5? Well, it would be 0 if you were on this part of the graph, and it would be a negative slope if you were on this part of the graph. But where are you? You're on that sharp corner where it's transitioning from the one to the other. So if I ask you what the slope of this part is, you would say 0. If I ask you what the slope of this part is, what is that slope? It's over 3 down 4, so the slope of that downslide part of the trapezoid is negative 4/3. But what is the slope, or what is the tangent line at that velocity graph point right there where that sharp corner happens? There is no tangent line. So f prime doesn't exist at that point. Now if I ask you, what's f double prime of 4, you would definitely say 0, wouldn't you? In fact, if I asked you any of these, if I asked you f double prime of 3, f double prime of 4, f double prime of 4.5, those would all be 0. But when you get to 5, that's a sharp corner. Derivative doesn't exist there. So where else would the second derivative not exist? There's a question for you. Yes, at 2, at 8, at 12, yeah. Yeah, and the endpoints, those are endpoints where I've chopped off the graph. We'll just talk about interior points. And if we do that, I agree with your 2 and your 5 and your 8 and your 12. What can you tell me about f double prime on the interval 8 to 12? Okay, James says negative 1/2. Everybody agree with that? So what is f double prime on that interval? It would be the slope of that curve. And of course that curve is just a line. It's the same line everywhere from 8 to 12. It's over 4 down 2. That definitely sounds like negative 1/2. What's f double prime on 12 to 15? Agreed. So what does that tell you about f? Let's say at t equals 12. What's going on with big F at t equals 12? And remember, big F is a graph we're not seeing here. We're just inferring things about the graph of f. What happens when the second derivative of a function changes signs? Okay, there's an inflection point for sure. If your second derivative goes from negative to positive, and the place that it happened was at 12, that means you have an inflection point at t equals 12. Okay, so what would the interpretation be there? Well, what was going on from 0 to 8? And I think we can kind of summarize everything now. From 0 to 8, we were adding up area. What happened starting at 8? We started taking away area that we had already accumulated. Okay, from 8 to 12, what are you doing? You're taking away area because f prime is negative. But we've also determined that on that interval 8 to 12, that your second derivative is also negative. So if you're taking away area, and your second derivative is negative, what does that say about how you're taking away area? Everybody agree with that? Faster? I mean, think about it. When you go from 8 to 12, you're taking away area, but can you see from the picture that you're taking away more area the further to the right you go? Those V values are becoming more negative as you go from 8 to 12, which means you're subtracting more the further you go. But what happens on the interval 12 to 15? Well, those V values, which are the F prime values, are still negative, correct? So that means you're still subtracting area, but aren't those values getting bigger or less negative, let's say? So I would say from 12 to 15, the amount that I'm subtracting from the accumulated area is actually decreasing, which means I'm still subtracting area, but I'm doing it more slowly. And that's clear, especially if I think about what the second derivative is doing. It's positive. And if we think about those old combinations we talked about back in chapter 2, what happens when f prime, which is your velocity, is negative, and f double prime, which is your acceleration, is negative? Well, then you're doing whatever you're doing faster, if those two are the same sign. On the right over here, we're saying f prime is negative, which means velocity is negative. We're saying f double prime is positive, that's acceleration. If those two are different, it means you're doing what you're doing more slowly. Okay, last question for you. What is f of 15? That down. Everybody agree with that? Does everybody see how Ethan's getting both of those? Remember where that one comes from. That was the area under the trapezoid part, which was the integral from 0 to 8 of the function. Okay, what's this 7? Does everybody see that that's the area under, or let's say above the triangle part? And of course, what's that triangle? It's 8 to 15, so it's 7 across. The height of that triangle is from the t-axis down to -2. And then of course it's 1/2 times that, so that would be 7. And of course that would give me what? 11 halves minus 14 halves. Looks like minus 3 halves. So the only thing I don't like about that in this picture, that doesn't seem to jibe with the picture. Eight, 3, 11. Oh, I'm sorry. I made a mistake earlier. Check the area on that trapezoid again for me. I think you trusted me on something there you shouldn't have. Try that again. What's the height? Yep. And then we said the two bases were the bottom, which was the 0 to 8, and the top, which is that little segment up at y = 4 there that goes from 2 to 5, which is 3. So of course there was 11 halves, but I think instead of multiplying I divided. So it should be 2 times 11. It should be 22. Okay, now, why did I catch my mistake? I was coming up with f of 15 was a negative number. Now what is f of 15? Geometrically it's supposed to be that area under the trapezoid minus that area under that triangle. I mean if my proportions are correct, which they are because this is the computer graphing this, not me, it looks like that area under that trapezoid is definitely bigger than that area under that triangle. So if I take the area under the trapezoid and subtract the triangle area, I shouldn't get a negative number. Okay, so this time it looks like I'm going to get 15. And what that means is what? My total displacement would be 15 feet. Meaning what? From time 0 to 8, we went 22 feet to the right. Then from time 8 to time 15, we went 7 feet backwards, which means my final position is at 15, which means my displacement is 15. Versus, what's the total distance traveled? Agreed. Does everybody see that? The area under that first part of the curve, which is the area under the trapezoid, that is the displacement from 0 to 8. It's positive 22, and since the velocity is completely positive everywhere from 0 to 8, I know that means all of the motion was directed in one direction. So let's say it's to the right. That means I would interpret that 22 feet of displacement as total movement in one direction, 22 feet. Okay, since your velocity is negative everywhere from 8 seconds to 15 seconds, that means the motion is all in one direction on that time interval. The area above that triangle is the displacement over that time. And it's all in one direction, and it's moving in the opposite direction, let's say to the left. So 22 feet to the right, then 7 feet back means the total distance you traveled is 29. But that's different than your displacement, which is the net change in your position. Net change in my position is 15 feet. I started at position 0, I ended at position 15. My net displacement is 15 feet. Making sense? Maybe sorta? Okay, you've got a couple of these questions in your online homework, also a couple in the book. Obviously I'm giving you lots of license here to not do every single thing in the book, but you should do the 2 or 3 of these that are in the book in addition to the ones in the online homework. Since there aren't many of these, I think doing the few that you have is important so that you get some practice looking at these pictures and answering these kind of questions. But these are similar to the kind of questions you're going to see in the homework. Various velocity and acceleration questions, displacement questions, distance traveled questions, and so on. Sure thing. Okay, let me stop the recording here.